What is up, team? I am the Masters Math Teacher, and in this video we're going to be learning about inverse functions. So jump on board and let's get into it. So like usual, we're going to work on the definitions of this sentence. So inverse functions. The word inverse essentially means opposite. So if we're dealing with the inverse of a function, we're dealing with the opposite of that function. So remember when we normally have an ordered pair, we have it as x, y. So our normal ordered pairs are x, y. When we're doing the inverse, we actually switch them. So this pair becomes y, x. So the x coordinate of the new one is y coordinate of the original. The y coordinate of the inverse is the x coordinate of the original. So let's see what I mean by that. The point 4, 1. If we find the inverse of this coordinate, we end up with 1, 4. Let's do another one. 2, 3. The inverse of this is 3, 2. Okay, let's see that on a graph. Okay, so I'm going to highlight the originals in yellow. And I'm going to highlight the inverses in green. Okay, so let's plot these. We've got 4, 1. We're going 4 across and 1 up. This is our original, 4, 1. The inverse of that is 1, 4. So it's up here. 1, 4. And I'll highlight these. We've got the yellow and we've got the green. The next one, we've got 2 across and 3 up. So about here. 2, 3. The inverse of this is 3 across and 2 up. So here. 3, 2. Now what you might actually notice about this is they're essentially reflected over some imaginary line. Now this imaginary line is actually the line of y equals x. So this line here, the line y equals x. So what you'll notice is all inverses are essentially a mirror image over the line y equals x. And that makes sense, right? Because the y is now the x. The x is now the y. So it's been reflected over this line. So let's take a look at this with a function. So let's look at f of x equals 2x plus 4. Let's sketch this. So we know it's a normal graph. It's got an intercept at 4. And it's got a steepness of 2. So I'm going to draw this in blue for the original. Blue for f of x. And it's going to look something like this. Okay. Now, let's find the inverse of this. So we know this is the same as y equals 2x plus 4. If the inverse means that x becomes y and y becomes x, what we can do is the inverse function here, and I'll put a red inverse function, inverse. What we can do is wherever there's a y, we replace it with x. Wherever there's an x, we replace it with y. So this is our inverse function. However, I can't graph that. X equals 2y plus 4, that doesn't make sense. We always need something y equals. So what we have to do is rearrange this. So I take the 4. So we got x, take 4 equals 2y, and then we divide by the 2. And now I'm going to divide each term by 2 here. And so we've got x over 2, take 2 equals y, or y equals x over 2, take 2. Now this looks better. So in my red, I'm going to be able to sketch this. I'm going to be able to sketch my inverse function. My intercept is at 2, -2. And it's got a shallower gradient, a much shallower gradient. It's of a half. So it's going to look like this. Okay. Now if we draw that dotted line, the y equals x line, you can see that every point, my drawing's a little skewed, but every single point is an exact reflection over this line. Every single point is a reflection over this line. And that's what an inverse means. Now some notation for this. What we do, if f of x is the original function, we denote the inverse with f -1 of x. And it equals x over 2 plus take 2. So this is our inverse function. Okay, that's our notation for inverse. So if f of x equals the original, then f -1 of x is the inverse. The same applies if the letter was g or h. It would be h of -1 or g of -1. Now there's a few rules that apply with taking the inverse of a function. The first rule to do with inverse functions, we can actually tell based on the name of it. Now recall, we're always calling these inverse functions. Inverse functions. Now recall, how do we know something is a function? Well, it has to pass the vertical line test. So if it has to pass the vertical line test, so the reflection, the inverse function, has to pass the vertical line test. So let's take a look at this. If we had the graph y equals x squared, the normal graph y equals x squared, we know that's a function, right? It's just an ordinary function. If we took the inverse of this, so if we went across the y equals x line, and we found the inverse, if we reflect every single point, so this point goes over here, so it'll end up looking like this. Of course, it will meet at the same point there. Well, what about this guy? What about the left-hand side? Well, it also reflects over, and it actually takes the form of a sideways parabola. But hold on, this doesn't pass the vertical line test. If we draw our vertical lines here, we hit twice, even though the original was a function. So in order to have an inverse function, the original graph must be 1-to-1. So for a graph to have, an inverse function, the graph must be 1-to-1. Must be a 1-to-1 function. Okay, so it has to be a function and it has to be 1-to-1. All right, so that's our rule for finding an inverse. For a graph to have an inverse function, the graph must be a 1-to-1 function. Okay, and we can see that based on our x squared graph. It just doesn't work. It can't have an inverse function because when we flipped it, it doesn't pass the vertical line test. And that is only because x squared was not 1-to-1. Now let's look at something a little bit more interesting about inverses. So we found out that x and y switch. But what happens to the domain and range? Well, if every single y value becomes the inverse's x value, then that must mean that the range of the original, so the range of f of x, it becomes the domain of f -1 of x. So they switch, the range and domain switch. So then we have the domain, or the dom, of f of x must then become the RAN of f negative 1 of x. Now there's a handy table to work that out with, and I always like to use this. We write f of x here, f negative 1 of x here, dom up here, and RAN up here. Draw our little table. And what we can say is the dom of this is now the RAN of this. It switches. The RAN of this is now the domain of the inverse. And so we can highlight these boxes to show that they are the same. And if you write this down with every single question, if you fill in the domain and range you know, you then can find the domain and range of the one you don't. So if you have the domain and range of the original, you can switch it to find the domain and range of the inverse. If you get given the domain and range of the inverse, the same thing applies. You can switch it back. It becomes the range and domain of the original. So let's put that into practice. Let's take a function, and I'm going to use our function notation here. So a function f such that the domain 0 to 4 gets mapped onto planar reals, and the function is 3x take 4. Okay, first things first, let's sketch this guy. So once we sketch it, we can figure out some more info. So what do we know? We know the intercept is negative 4, so it's down here. And we know the gradient is 3, so it's sort of steep. So it's going to look something like this. However, it's restricted. So we draw our red barriers. We've got a barrier at 0 and a barrier at 4. This is x equals 4 and a barrier at x equals 0. We've got a solid dot on this barrier here and a hollow dot at that barrier there. So let's find out these points. Well, we already know that this one is negative 4. That's because we knew the intercept was negative 4. So for our RAN is going to be negative 4 inclusive of, because we included 0, and it's going up to this point x equals 4. How do we find the y coordinate? Well, we substitute it back into the original. So y equals 3 times 4 take 4. So y equals 12 take 4, which equals 8. So our RAN goes up to 8 with a circle bracket because we do not reach 4. All right, so now let's try find the inverse function. So our original function is y equals 3x take 4. For the inverse here, we switch our x and y. So we've got x equals 3y take 4. Then we have to solve this so that we can graph. So we plus 4, x plus 4 equals 3y, and then we divide each term by 3. So we have y equals x over 3 plus 4 over 3. If we want to write that in inverse notation, we get f negative 1 of x equals x over 3 plus 4 over 3. All right, let's sketch all of this together and then find our domain and range. So I'm going to draw a new graph here. I'm going to take the original blue, except I'm going to take the restricted blue. I'm not going to take the full graph, I'm just going to take the restricted blue here. So from negative 4 up to 4, 8, 0, 4 here. I'm just going to connect them up. Much straighter than that, hopefully. Okay, that's our straight line there. Now, let's sketch the other one. So let's color this in green, we have the y-intercept is 4/3, so it's going to be about here, 4/3, and it's going to be a much shallower graph. So it's going to look something like this. But what is its domain and range? Well, if we look back at our guide box here, what we can do is fill in what we know. So we know the DOM of the original. If I get rid of this circle, I'll keep the colors. But if we get rid of the circle, our DOM here is 0 to 4. And our RAN is -4 to 8. So now following our guide here, the domain of our inverse is the range of our original, so it is -4 to 8. So our domain of our inverse is -4 to 8. When we're looking for the range of our inverse, it is 0 to 4, because it is the domain of our original. Now we put those back into our green graph, find the walls. Got a wall at -4 and a wall at 8. However, we actually do not need to plug these values in. We can actually find out, based on this, what our coordinates must be. The lowest value of our domain is -4. Our lowest value of our range is 0. Because it's a linear graph, this must occur at -4, 0. Again, with our range and our domain, comparing them, the top value is 8 for our x and 4 for our y. So this point here must be 8, 4. Do you notice anything interesting about those 2 points? Compare them with the 2 points on our blue graph. Sure enough, they are exactly switched. These two have switched, and these two have switched. And that's because of the reflection. So if you find the endpoints for one of them, you do not need to plug in the walls for the second one, you just need to do the old switcheroo. Alright, let's do one more here. We're going to do the function f such that we're going from 3 to infinity, mapping onto reals, and we're going to take the function f of x equals x take 2 squared plus 3. First things first, sketch it. So we grab out a graph. Now this is a parabola. We know its turning point is 2, 3. So we're going to put it at 2, 3. And we know it's a smiley face parabola. So it looks something like this. However, we've restricted our domain. So let's actually plot that point. It's going to be 2, 3. Now we grab out our red for our wall, and we're putting it at 3. So it's actually past the turning point. And this is a very important part as well. We'll explain that in a second. So let's find what point that is. Well, we plug it back into the original. So we're going to go y equals 3 minus 2 squared. So we're plugging in x equals 3 plus 3. Solve that out, we get 1 plus 3. So y equals 4. So this point here is 3, 4. And now it goes all the way to infinity. Alright, so if I grab a new graph out, so I can fully sketch this, our starting point is at 3, 4. So 3 across, 4 up. And it looks something like this. And it's a bit more curvy. It's not a straight line because it's still a parabola. I might actually make this a bit more steep here, just to show you. So, when we're looking at this, remember when I said the function must be 1 to 1 for it to have an inverse? if we look at the original graph, yes, it's a function. However, if we did our one-to-one test, our horizontal line test, this hits twice. So the original graph, f of x equals x minus 2 squared plus 3, is not one-to-one. However, once we've put in these restrictions, this new graph is in fact one-to-one. And so after the restrictions, this graph does in fact have an inverse. So we can find the inverse for this guy. So let's do that. Let's find the inverse. So our original graph is y equals x minus 2 squared plus 3. We switch our x and y's when we're finding the inverse. So we go with x equals y minus 2 squared plus 3. Now we just solve this out for y. Minus 3, x minus 3 equals y minus 2 all squared. Now we take the square root. Now remember, whenever we take the square root, we have to do plus or minus. It was y minus 2. And finally, we get 2 plus or minus the square root of x minus 3. That's by adding the 2 across. Equals y. All right. That's not quite finished. Can we try figure out why? Give it some thought. So, do we have any y values less than 2? So what I mean is, can we actually have that negative? Do we need this minus there? Well, let's check our range. What is the range for our inverse? How do we find it? Well, we make our table, f of x, f negative 1 of x, dom, ran. We're in our table here. The domain of f of x was 3 to infinity, and our ran of f of x, so we haven't explicitly stated the range. But can we quickly find that? Well, let's have a look. At our original graph here, remember the wall actually started at 3, 4. So I've actually drawn this blue graph slightly incorrect here, as you can tell. That point should be the red point that we found earlier. So it should be the point at the wall. So let me fix that up here. This will actually be our 3, 4. Just remember, this is not the turning point. The turning point was actually down here somewhere at 2, 3. This is not the turning point. So our range for our original is actually going to be 4 all the way up to infinity. So our range is 4 inclusive, because we let it equal 3, all the way up to infinity. So how do we find the domain and range of the inverse? I want you to pause the video and give it a shot. So all we do is we switch them. So the domain of our inverse is now the range of our original, so 4 to infinity. The range of our inverse is the domain of our original, so 3 to infinity. So now back to my original question. Can we have that minus? This minus over here. Can we have it? Well, let's check our range. The lowest possible value for our y is 3. So that means 2 minus nothing can equal 3. We cannot have 2 minus a positive value out of our square root equaling 3. So that means we must only have the plus here. So this is actually just going to be 2 plus root x minus 3. And that's because we don't need the minus, because it's not part of our range. That's irrelevant. So now let's sketch that fully. Well, we can actually see based on this thing, we know where it starts. It starts at 4, 3. So let's plot that. I'll use my red here. It starts at 4 across and 3 up. So it's going to start here. And we know it goes to infinity. So it's going to look like this. And it's a square root graph. And you can kind of tell, if we flip that over the y equals x graph here, that's exactly what happens. It starts at 3, 4. This switched to 4, 3. And then it departs. It sort of branches out away from the y equals x line. Now you have all the skills required to tackle questions involving inverses. I'd wish you luck, but I know you don't need it. So go smash out some mathematics. And as always, if you liked the video, give it a like. If you didn't, give it a dislike, and let me know in the comments what I can do better. If you have a topic you want me to cover, let me know in the comments below.